Thank you, Professor, and all attendees. My name is Anand Akash, and I am presenting today on the design and performance analysis of hydrogen liquefaction process. The contents of my presentation today is, first of all, I will introduce about hydrogen, a basic introduction of hydrogen supply chain, hydrogen transportation, and then move to main topic of hydrogen liquefaction. And hydrogen liquefaction introduce different scenarios. I will discuss about the introduction, orthopara isomers, its process design and simulation, and at the end, in the conclusion, I will present what the process results. So, first of all, introduction. Hydrogen, as we know, is an energy carrier, and we call it as a clean fuel, because when it burns, there is no CO2 emissions. But as of now, 2022, hydrogen is mainly produced from fossil fuels. This is a major problem with the hydrogen supply chain. Because itself, if hydrogen is produced from fossil fuels, it generates CO2 emissions. So the major source of hydrogen production today is natural gas. Around 76% hydrogen is produced, and from coal, around 23%. Hydrogen can be integrated with different industries in transportation, as a fuel, and with the renewables. So it can reduce the emissions of CO2 from its, if we use hydrogen in as a fuel or as an energy carrier. So a brief introduction of hydrogen supply chain. Hydrogen, as I mentioned already in previous slide, hydrogen is produced from fossil fuels, but it can be produced from renewable fuels also. So the production process involves, if it is produced from renewable fuels, from biomass or bio-waste, it needs a conversion process or electrolysis process, or it can be, if it is produced from fossil fuels, through steam methane reforming, hydrogen is produced. The processing is the next step is after production. The next step is the processing of hydrogen gas. If it is used in which form, like if it is used in compressed or in liquid form, so it is converted into compressed gaseous hydrogen or liquid hydrogen. Then it is transported to different end users through ships, through trailers, through pipeline. If it depends on the mode of transportation and its end users. And it is after transportation, its storage is maybe in form of gaseous or liquid, and it can be utilized in industries, in power sector, in transportation industry. So hydrogen transportation. Hydrogen transportation is actually the transport of hydrogen from one place to another place, and it depends on the end user requirement of hydrogen, whether it is used in gaseous form or it is in liquid form. So it depends on the target's requirement. It depends on the consuming behavior, whether it is consumed in high pressure compressed gaseous form or in a liquid form as it is, or depending on the end user's requirement and the mode of transportation. There are three main pathways to transport hydrogen: either in gaseous form through pipelines, in liquid form through ships or tankers, or material-based hydrogen. The material-based is in the form of hydrates, or it converts into ammonia or a liquid organic hydrogen carrier. Okay. So the three main delivery ways is obviously even if it is in liquid form or gaseous form through pipelines, or liquid form through ships. These are some of the basic worldwide hydrogen projects. Around 20 largest giga-scale hydrogen projects installed worldwide. It's in Australia, Russia, some in the Middle East, Saudi Arabia. So based on this hydrogen demand and hydrogen recent attention, which is again worldwide in the recent times. We can see that in the future hydrogen has a bright future in terms of its usage, in terms of clean energy fuel. In this also we can say that this is a brief demonstration of hydrogen projects and in which hydrogen is delivered from one country to another country, from Australia to Japan, South Korea, or from Middle East. So hydrogen transportation from one country to another country has recently gained attention very much. Based on this hydrogen transportation, we have different modes of transportation, as I mentioned earlier. Liquid hydrogen, liquid organic hydrogen carrier, LOHC, gaseous hydrogen pipeline form. This is the economics of the hydrogen transportation, which form of transportation is better for hydrogen supply chain. As we can see that if the distance of transportation increases, okay, the hydrogen in the form of liquid or ammonia or LOHC shows cost benefits as compared to if pipelines. If transportation, hydrogen is transportation, for example, 1,000 tons per day, and in this case, hydrogen, liquid hydrogen above 4,400 kilometers is economical. If gaseous hydrogen will not be economical if we have a long distance in large volume and long distance transportation. This is another demonstration of why liquid hydrogen is economical. Because of this, main volume reduction of hydrogen. If hydrogen is compressed to 200 bar or 700 bar, which is the common design pressure of hydrogen storage, hydrogen volume is reduced to 180 times or 486 times as compared to the 1 bar. But if at 1 bar, if hydrogen is liquefied, the hydrogen volume is reduced to 886 times. So that's why it's because in liquid form it can transport a huge volume in the same space. It shows that liquid hydrogen will become economically efficient if we have to transport over long distances. In this case, in this graph, we can also see that this x-axis is the energy content on the mass basis, and this is the hydrogen graph, and we can see that hydrogen on a mass basis has a higher value as compared to any other fuel, methane, LPG, gasoline, diesel. So the main purpose of hydrogen transportation in the liquid form, we can see that hydrogen gas is, this is a basic diagram of hydrogen liquefaction, how we liquefy hydrogen, considering the importance of its liquefied hydrogen transportation. We have a hydrogen gas, and it goes through a heat exchanger, and then it is liquefied with the help of these refrigerants. This is the simple liquefaction process of any gas. But in the case of hydrogen, it is not as simple as it seems. Why? Hydrogen liquefaction is quite a unique process as compared to any other gas process. Because hydrogen in its natural form exists as ortho and para isomers. At 25 degrees C, hydrogen exists as a 75% ortho and 25% para. If we have to liquefy this hydrogen, this ortho hydrogen and para hydrogen composition will change. And at minus 253 degrees C, which is the boiling point of liquid hydrogen, hydrogen exists as 1% ortho hydrogen and 99% para hydrogen. So we need to convert this hydrogen, para hydrogen, to maintain the equilibrium at these conditions, and we need reactors to do that. This graph simply shows that as the temperature changes, the composition changes. So if we cannot convert this hydrogen, hydrogen will eventually boil off and we have losses, and it cannot be stored for a long time. So we need to convert this para-hydrogen from 25% to 99% if we have to store liquid hydrogen for a long time or for a long distance transportation. So this is simply a process simulation diagram, simplified form of process design and simulation. We can see that this is the field conditions of hydrogen. Hydrogen at 25 degrees C and 21 bar exists as a 75% ortho and 25% ara. So the gaseous hydrogen passes through heat exchanger, and then we convert this para-hydrogen to increase the composition of para-hydrogen from 25% to 99% through ortho-para conversion reactor or OPC reactor. And then we further liquefy it and transport it in liquid form. The end composition of hydrogen is simply 99% para-hydrogen and 1% ortho-hydrogen. But the major problem with this is ortho-para conversion is exothermic reaction. Ortho-para conversion, when we convert this para-hydrogen from 25% to 99%, it releases heat. So either we have to account for this heat during this liquefaction process. In industrial processes, catalyst is embedded inside this heat exchanger to promote this conversion, ortho-para conversion in industrial processes. To mimic the same industrial process as in process design and simulation, we have designed a process in which ortho-para converted, and the extra heat load which during this ortho-para conversion is again we have looped this stream so that the same exchanger bears the heat load of this ortho-para conversion. This is called adiabatic conversion. But in another case, if we do not have looping or this kind of looping for this hydrogen, we can have isothermal reactors. Still we have ortho-para heat, and we have to provide this cold energy to remove this heat, ortho-para heat, from outsource. We can use liquid hydrogen, liquid helium, liquid nitrogen, depending on the temperature of this hydrogen stream. So after the design of the process, we got some results, and the energy analysis results of the process shows that in isothermal process, the energy consumption, SEC, is specific energy consumption, kilowatt hour per kg. It's unit, and it shows the energy consumption of 6.9 kilowatt hour per kg. In case of adiabatic process, the energy consumption is 12.2 kilowatt hour per kg. As I mentioned earlier, we have ortho-para conversion. So the final composition is 99.7. That meets the equilibrium data, and validated against the experimental data of this conversion, ortho-para conversion. We can see that the isothermal process is quite efficient if we compare the commercial hydrogen liquefaction process installed worldwide. Commercial hydrogen liquefaction process energy consumption SEC ranges from 12 to 15. So we have quite low in case of isothermal, but in case of adiabatic, then we have looping. Then the energy consumption increase because we have extra heat load and extra refrigerant quantity we require to cool hydrogen. So that's why the energy consumption is high in case of adiabatic process. Thank you.
질문 있나요? 예.
Okay, thank you for your presentation. And I found that from your presentation, actually, commercial SEC there is about 12, but your presentation shows that it's much less than that. And what is to elaborate a little bit more why you have that much lower specific energy consumption compared to the commercial one?
Okay. This is in similar to commercial process, it's 12.2, but in case of this isothermal process, it's 6.9. It's lower than commercial process. And if we see the configuration of isothermal process, as you mentioned, when we have hydrogen gas and we have to convert this orthopara combustion, it releases heat. This heat is absorbed by external source. We provided external refrigeration to absorb the heat. This heat is not accounted for in this 6.9. If we account for this 6.9, it may increase to around 10 or 11. But if we do not account for this heat in the energy consumption calculation, then it will drop down to 6.9. It depends on the configuration of how you change configuration and how you have installed at which temperature state this orthopara conversion.
Thank you.
혹시 추가적인 질문 있으신가요? 예. Thank you for your good presentation.
Thank
you. Big applause again, once again.